Hi, and welcome to this video tutorial series where I'll be showing you guys some cool new features on the analog to digital converter with computation featured in the new PIC18F Q10 product family. In this first video, I'll be showing you guys how easy it is to use the base functionality of the ADC and how easy it is to graph that using the Power Debugger and the Data Visualizer tool. So let's get started. So here we have the Curiosity HPC development board set up, and in this video we'll be using the onboard potentiometer as our analog sensor. Now this white wire here is connecting the transmit pin of the EUSART on this device to the CDC virtual COM port input pin on the Power Debugger. Then we also have a ground and VDD coming in from the device onto the ground and ref pins. So the first thing I've done in MPLAB X is open up a new project and selecting the PIC18F 25Q10 device. I am using the XC8 Pro Compiler version 2.0, and I've opened up MCC. So we're looking at the system module, and what we got to note here is that we don't have an external oscillator connected, so we need to change this into the high frequency internal oscillator. And then we need to add our peripherals, and of course we need the ADC. So the ADC is not going to do a lot more than its actual base functionality, so the only thing we really need to take a look at here is the acquisition count. The acquisition count is the time that the ADC is going to let the sample and hold capacitor charge before making a conversion. So it's important in terms of accuracy, but as long as it's above some minimum level, then it should be fine. So if you need to have a super fast execution of the ADC, then you need to look in the datasheet to find the math to figure out how much this needs to be, or what's the minimum value for this to achieve your accuracy. Now in this case, we don't need that, so we'll just overdo it a little bit and use 5 microseconds, which is more than enough. Then we can add the EUSART to transmit our data. So we need the enable transmit function here, and that's it. So everything else here is good as per standard. And then we can go over to our pin module to add the potentiometer. We can see here on the Curiosity that it's connected to pin RA0. So in MCC we can go over to our ADCC module in the pin manager and then find the A and X input row, so the analog input. And then we can see we have port A and pin 0. So this right here is our channel. Then we can rename this so we can reference our new name, in the code later for simplicity. So now we can generate. Alright, so now that it's done generating, we can exit MCC and open up our project. So here we have the main file that MCC has generated for us. Now the first thing we want to do is we want to create a variable to store the ADC results in. So we have a 10-bit ADC, so we can't use an 8-bit integer, so we need a 16-bit instead. So uint16_t, and then we'll just call that ADC result. Then we need to feed some values into this new variable. So we'll go into our while loop and then write ADC result equals. And then we'll use one of our new functions that MCC has created for us, so ADCC_get. And then if we don't remember the full function, then we can hit Control Spacebar to get some suggestions. So we'll use the get single conversion, because then we'll get one conversion per time it goes through the while loop. And then we need to write a channel, so the channel that we just created should do it. So at this point we have the values coming in from the ADC reading the potentiometer, and we need to send this over the EUSART to the Power Debugger in order for it to be read by the Data Visualizer. So first of all, we need to find out how the Data Visualizer wants to receive its data. And we can find that in the Data Visualizer User's Guide. I'll put a link in the description box for how to find this. And you can also, by the way, find this in the in the Data Visualizer. If you open up the configuration menu and hit this question mark right here, then you'll get the Data Visualizer User's Guide. So if we open up protocols and the data stream protocol, then we can see here in the stream format, this is how the data visualizer wants its data to come in. So first of all, we can see that it needs to have a start frame and an end frame. So these are just 1 byte per on the start end and on the end of it. And these can be anything as long as they're bitwise opposite of each other. So we'll go back to our code and we'll define those. So start frame. And then we can call that anything, so 77, 0x77 for example. And we'll define the end frame. End frame. And for simplicity, we can just do the opposite of the start frame. And then we can write that to the USART. So we'll write USART, SART1. And this is also one of the functions that MCC has created for us. So EUSART write, and then we'll write the start frame. And then we can just copy this and write the end frame as well. All right, so next up is the contents of the message. So we have ADC results from multiple sources if we have that. We only have the one source right now, so we'll write that. Then we also have a prescaler, but we don't need that right now. We just want to read the data as they are. So we need this thing right here. So we're going to write the results as is, almost. The only thing we got to note here is that we need to write this in little endian, meaning that we need to write the low byte before the high byte. So in the code, this means that we'll do a normal EUSART write, and then ADC result. But then to get only the low byte first, then we can AND this with a full byte. And what this does is that the 2 top bytes, because we have 10 bytes, bits, the 2 top bits will be ANDed with zeros, while all the bottom bits will be ANDed with this full byte right here. So all of the bottom ones will be sent, while the top 2 will be 0, so they will not be transmitted. And then to get the top byte, we will also write ADC result, and then we'll just right shift that by 8 positions. And this will just push out the low byte off the end here, kind of, and then have the 2 remaining bits be sent over the EUSART. And then finally, we'll just put on a small delay to make sure that the Power Debugger and the data visualizer kind of keeps track of our data and doesn't lag or anything. So I'll just put on 10 milliseconds of delay there. Then we can save that and program. All right, so now that that's been programmed, we got one thing left to do before we can graph the data in the data visualizer. And that is to tell the data visualizer how to represent our data in the GUI. Now the reason why we do this is because if we have a lot of signals or different channels that we want to read from, then we might want to sort those signals in some way in the GUI so we can easily find that and graph it while we're there. Well, now we only have the one signal, but we still need that configuration file. So we can go into our data visualizer user's guide to find out how this is done. So right here you can see a list of different data types. And this is because we need to denote what kind of data type we will be sending so that the data visualizer will understand the data that comes in. Now we have an unsigned data type at least, and then we also have 2 bytes. So an unsigned short should do it in this case. And then we can see here in the example that the tag comes first, so this one right here. And then these 2 numbers are that's the position of the signal in the GUI. So we have, that's the matrix position. So position 1,1 will be in the top left corner. And since we only have the one signal, that makes sense for us. So we'll just use 1,1 for our case. And then this last part right here is just the name for the signal. So I've created this. We have the potentiometer file here, so we can just store that in the text file. Just save that and close it, and then we can go over to the data visualizer. Now the data visualizer is going to look a lot like this when you open it the first time. So the first thing we want to do is close down this DJI control panel, because we won't be using that for this video. And then we'll just open up the serial port control panel instead. So first we need to make sure that we have the power debugger connected. So just select that. And then we can see here that these values are good as standard, because that's also the standard for the EU SART in the MCC for this device. So then we can just connect that. And there we can see that we do have some data coming in. We can change that to hexadecimal values, and then we can see that these 77s right here, that's the start byte, and then this is the end byte. And then we have the data coming in between there. So then we can close that down and open up the protocols and then the data streamer. And this is where we insert our configuration file. So we will search for that and find it right here in that TXT. Open it up and then load. And then we can see that we have that signal that we put in that text file. We have the Potmeter right here. So then we can just drag the plug here from the serial port, meaning that the data stream coming in from the serial port will be connected to this data stream protocol that we have here. So this Potmeter signal is actually going to contain those values that we're sending. And then we can open up the graph and plug it in to new plot. And then if we twist and turn this Potmeter, then we can see that it is plotted in real time in the data visualizer. All right, so we can disconnect this for now and then come back to it later. And then we can go back to MPLAB X. So the next thing we want to do is we want to check out the accuracy of this device. So the way to do that is we will compare the ADC result measurement of the Potmeter with measurements using a voltmeter. So first of all, we need to figure out how to convert the results from the ADC into voltage. So we have a formula right here that says that we need the ADC result times the maximum voltage divided by the ADC resolution. So first of all, we need this ADC result right here. And to get that, we can add a watch of this ADC result here. So that means that when we debug, then we can read off, we can halt the operation, and then we can read what the ADC result is, what that variable contains. So we right click and hit new watch, then OK. And then we can add a breakpoint on the line below, because then when the code reaches that line, then we know that this function right here has been executed and that the result in ADC result here is going to be new. So then we can start debugging. All right, so now that we can see that the target has been halted at that line, and we can go into our variables tab here. And then we can see that we have 512 on our ADC result. And you can see that that makes sense because the Potmeter has been set to about the middle. We have 1,024 values, so this is pretty much dead center. So we can note that down, that we have 512. We can do that on the calculator, for example. 512. And then we need the maximum voltage. And right now we can see here on the curiosity that we have set it to run on 5 volts. But since the voltage source coming in from the USB might have some inaccuracies, we kind of want to measure this using the multimeter just to be sure that it's correct. So we'll do that first. Let's see, we'll measure across VDD and ground. And here you can see that we have 5 volts, 5.1 volts. So I have 512 times 5.10. And then we'll divide that by the ADC resolution, which is 10 bits, which is 1024 different values. But since we're calculating this with the ADC results, which starts at 0, so it's 0 indexed, we need to do that with this resolution as well. So this means that it's not 1024 values, it's 1023. That's the top value that we can get. So we'll divide that by 1023. Now we can see that the voltage measured by the ADC across the potentiometer is 2.552. So I'll just note that down. And then we can use the multimeter. I'll just move that over from the voltage from VDD over to the RA0, which the potentiometer is connected to. And we can see that our result is 2.549. So we are 0.003 volts off on our ADC, which is good enough. So now the next thing we want to do is we want to be able to graph this value directly. So because the ADC result isn't going to actually tell us a lot. So if it plots between 0 and 1023, then you don't really know how much voltage is going across this potentiometer. So now we want it to plot between 0 and 5.1 volts. So first of all, we need a floating point value for the voltage to be stored in. So we're going to call that voltage. And then after the ADC result has been measured, then we can say that voltage is equal to ADC result times 5.1 divided by 1023. So now we have the voltage, the actual voltage coming in here, but since this is a floating point, we need to treat this differently than the actual ADC result, which means that we can get rid of this stuff. And we still need the end frame, of course, and the start frame. And then we need to send each byte of the floating point, each one by one. So first of all, what we're going to want to do is, because we got 4 bytes in the floating point, so what we're going to want to do is make a for loop that iterates through each byte in this floating point value, and then sends them one by one. So that means that we want this voltage, this floating point voltage, to behave kind of like a list or kind of an array or something, so we can reference each and every one of them. So first of all, we'll make a pointer to it. So uint8, then we'll call that volt pointer. And then that is equal to uint8t, and then dereferenced voltage. So this will point to the voltage, and then this can be referenced as if that was an array. So we can say, for example, voltage pointer 0, and that will put out the 0 or the first byte of this floating point value. So inside our code, we can make our for loop. And then we also need an iterator, of course, and we will make that up here. So an 8-bit iterator called int8i. And then we'll say I is equal to 0 first, and then then we will run as long as I is less than the size of the float. Oh, look at that. There we go. So it's a float, and then it will iterate. All right. So inside this for loop, we can write to the usart. So usart 1 underscore right. And then we'll just do volt pointer. And then we'll reference that as if it was an array, so voltage pointer of I. Just like that. Now we can program. And of course stop the debugging first. And then we can program. Alright, so now that that's been programmed, there's one thing that we need to change, because if you remember the last time we sent some values, we made a configuration file and we told it that this was going to be a 2-byte unsigned integer. So we need to change that, because now we're actually sending a floating point value instead. So if you go back to the user guide, then we can see here that we have a floating point for a size of 4, and then we have a tag that is f. So f11 and then name. So it's basically the same as before, except we changed the d to an f. So I made another file here called voltage, and you can see here f11 and then voltage is the new name for it. Just save and close that, and then we can open up the data visualizer again. And then we can find our new file, voltage, open that and load it. And then we can see that we have this new voltage signal right there. So now we can drag this new signal into the input plug right here and connect again. And then we can turn the potentiometer to see that we have values between 0 and 5 volts. And this is consistent also with the potentiometer.